Today we're looking at lesson 22, solution sets to simultaneous equations. That means we have more than one equation at the same time, and we need to figure out an ordered pair that is valid for both equations, which means if we were graphing the equations, it would be the ordered pair where they cross. To start out, consider the following compound sentence: x plus y is greater than 10 and x equals 2x plus 1. Circle all the ordered pairs x, y that are solutions to the inequality x plus y is greater than 10. So I need to find x plus y is greater than 10. I'm circling them. 3 plus 7 is 10. Nope. 7 plus 3 is 10. Nope. Negative 1 plus 14 does work. That's 13. 0 plus 1, nope. 12 plus 25 works. 5 plus 11 works. 0 plus 12 is greater than 10. 1 plus 8 is 9. Nope. 12 plus 0 is 12. Yes. All right. So those all satisfy the inequality x plus y is greater than 10. Now underline all the ordered pairs x, y that are solutions to the equality y equals 2x plus 1. So let's look at these. I've got 7 equals 2 times 3, which is 6, plus 1 is 7. So that does work. I just did y equals 2 times 3 plus 1, and that does work. The next one, I've got y equals 2 times 7 plus 1. Nope, that doesn't work. How about xy? Y equals 2 times 0 plus 1. That works. I didn't check negative 1 and 14, sorry. 14 equals 2 times negative 1 plus 1. That does not work. Check this one. 25 equals 2 times 12, which is 24, plus 1. That does work. 11 equals 2 times 5 plus 1, that does work. xy. 12 equals 2 times 0 plus 1. Nope. 8 equals 2 times 1 plus 1. Nope. xy. 0 equals 12 times 2 plus 1. I said that backwards, didn't I? xy. Y equals 2 times 12 plus 1. Still doesn't work, right? And then negative 1 equals 2 times negative 1 plus 1, which is true. There we go. List the ordered pairs x, y from above that are solutions to the compound sentence x plus y is greater than 10 and y equals 2x plus 1. So I need the ones that are circled and underlined. 12, 25, 5, 11, and that's it. Just those two. List 3 additional ordered pairs that are solutions to the compound sentence. This is hard. I'm just trying to come up with 3 ordered pairs that also are solutions. I'll give you some, and you can just check them a little bit and show that they are. I'm coming up with 3 more ordered pairs that are solutions, and they do work. All right, sketch the solution sets to the inequality x plus y is greater than 10 and the solution sets to y equals 2x plus 1 on the same set of coordinate axes. Highlight the points that lie in both the solution sets. So I'm going to do that on pause, so you can go ahead and do that in your notes. All right, I graphed in red the inequality x plus y is greater than 10, and then I shaded everything above, and then I graphed the equality y equals 2x plus 1, and then I shaded in blue highlighter where the solution is. The solution is the intersection of the line and the shaded red area. Okay? All points. That was a mess up. There we go. All points that lie on the line y equals 2x plus 1, and above the line, y equals negative x plus 10. Okay, that's the description of the solution. All right, example 1, solve the following system of equations graphically and algebraically. So give me a second, I'll graph them. I have to put them in slope-intercept form first, and then I'll give them a little graph. Okay, I just need to let you know graphing with a stylus on an iPad is near impossible. Desmos is fantastic. I might use that on the next one, but not right now. Algebraically, I am going to combine these a little bit to solve one equation for another. The first thing I'm going to do is set the second equation into slope-intercept form. So let me rewrite that. X minus y equals 7. I'm going to solve for y, so subtract x from both sides. I have negative y equals negative x plus 7. Multiply everything by negative 1 or divide everything by negative 1. There we go. So I've got two equations, 1, 2. They're both set equal to y, so I'm going to head and set those equal to each other since I'm trying to find where they are equal, the ordered pair where they're equal. I can actually solve them both for y and set them equal to each other and then solve. So subtract x from both sides, I have x. Subtract 1 from both sides, I have x equals negative 8. And then plug that x equals negative 8 into either equation to solve for y. I'm going to plug it right into that one. Y equals, instead of x, I'm going to write negative 8 minus 7. So y equals negative 15. So my solution is negative 8, negative 15. And if you look over at my graph, you'll see I'm at least negative x, negative y. So negative 8, negative 15 is just about right for that. Okay? All right. Solve each system first by graphing and then algebraically. I'm going to graph it quickly on Desmos. To solve it algebraically, these are already set equal to y. They're both in slope-intercept form, so I'm just going to set them, oh, for goodness sakes, set them equal to each other. And solve for x, and then plug it back into an equation and solve for y. First of all, I don't like fractions. I'm going to multiply everything by 2 and get rid of that. And now add x. I also don't like negative variables, right? Add 2. So x equals 2. Plug it back into either equation. I'm going to pick the one without the fraction. Y equals 4. Instead of x, I'm going to write 2 minus 1. So 8 minus 1 equals 7. My ordered pair is 2, 7, x, y. And there you see my graphical solution. Okay, and it does support my algebraic solution. Pretty cool. Okay, letter B, solve each system first by graphing and then algebraically. Let's look to graph first. I'm going to put this in slope-intercept form. Y equals negative 2x plus 4, and the second one, 3y equals negative 2x plus 9. Divide everything by 3. So I'm going to graph those two, and I'll be right back, okay? You can graph them also. Okay, there's your graphical answer. Now that I have them both set up as y equals, I can set them equal to each other so that I can solve for x and then use our x to solve for y. First thing I'm going to do, I hope you guys are guessing, I'm going to get rid of that 3 by multiplying everything by 3. Did I do that right? I think so. Yep. All right. I don't like negative variables. Strange that way. So I got rid of the negative 6. 5x equals 3/4. Yucko. Plug that back into an equation. Let's see. Doesn't really matter. They're both a little bit messy. I'm just going to go for the first one. Instead of x, I'm going to write 3/4 plus 4. Now you can get out your handy-dandy calculator. 3/4 times 2 is going to be negative 3/2. Negative 3/2 plus 4. I need to change that into a fraction. I'm going to go 8/2 because 4 is the same as 8/2, which gives me negative 3/2 plus 8/2 is 5/2. So my ordered pair is 3/4 and 5/2. Cool. I don't like that one either, but messy fractions happen sometimes. Okay, last one. I'm going to put them in slope-intercept form and graph them. I'll be right back. So it doesn't look like I have a solution. I have different y-intercepts and identical slopes, so I think I have parallel lines here. I should be able to prove that algebraically, right? I should get no solution. All the x's cancel out. I'm left with 5 equals 8, which is not true. Therefore, I have no solution. So I can show no solution graphically, and I can show no solution algebraically. Right, next example. It says, suppose you have a system of equations from exercise 1, part C, instead of inequalities. So now suppose the system of equations was instead a system of inequalities. Sorry, I missaid that. I'm going to graph those again and show you what our solution really is. Okay, so, well, if we remember, this first equation was y greater than or equal to negative 3x plus 5. If I go ahead and test the point 0, 0, the origin, I'm going to get y is greater than or equal to 5. Is that true? No. This is my first equation. So I don't want 0, 0 to be a part of this solution. So for the red, I'm going to shade not 0, 0. Alright, and for the blue, I'm going to put it in slope-intercept form again. Y is less than or equal to negative 3x plus 8. Test the origin. I get 0 less than or equal to 8. That's true. So for that one, I'm in blue. So I'm going to shade including the origin. Now, the solution to the set of inequalities is actually everything in between the lines where they overlap. So that is your solution. Your solution set is the lines and everything in between. Graph the solution set to the system of inequalities. I'm going to put it in slope-intercept form. I get negative y less than negative 2x plus 3, multiply everything by a negative 1, and have to flip my inequality. Oops. And my other one, let's see, minus 4x both sides. I have 3y greater than or equal to negative 4x. Divide everything by 3. Y is greater than or equal to negative 4/3 x. All right, I'm going to graph, and I'll be right back. All right, I'm going to test my zeros. For this first equation at least, I get 0 is greater than negative 3, which is true. So I'll go ahead and shade that. I want to shade everything including the origin because it was a true statement, right? Now for the blue line, it's not quite as simple. Y is greater than or equal to negative 4/3 x, so we're going to shade where my y is positive. Okay, everything above the line where y is positive. And my solution for the set of equations, or the set of inequalities, is where they overlap. Now, if you guys want colored pencils to work on this in class, I've got some, but there's our solution. Exercise 2, graph the solution set to the system of inequalities. These are our last two examples. I'm going to go ahead and put them in slope-intercept form, and I'll be right back. All right, let's graph that red one first. I'm going to go down to -5 for y-intercept. 1, 2, 3, 4, 5. A slope of 1 over 1. Draw my line, which usually takes me a few tries. That's not too bad. Do my test point of 0, 0. Try to make it a legible 0, 0. Is 0 less than -5? No, it is not. So we want to shade below that line where 0 is not part of the solution. All right, x -1. Let's see. I'm going to the -1 for x. That is incorrect. -1 for x, and draw my line. Oh, dadgummit. That is supposed to be a dotted line or dashed line. I was not paying attention. I'll make this one a dashed line. How about that? I thought lines were hard to draw on an iPad with a stylus. It's harder when you're dashing them. Now we're going to shade everything where x is bigger than -1. And then where your intersection is. There you go. Last example. I have 3 equations now. I'm going to graph the lines. I'll be right back. Well, let's do this. I've got my red one. Oops. Y less than or equal to x plus 4. If I test my 0 on my origin, is 0 less than or equal to 4? Yes. I'll have y is less than or equal to -x plus 4. I just put those in different orders. And then y is greater than or equal to 0. Okay, let's do that y is greater than or equal to 0 first. My line is going to be right there, solid, and I'm shading everything above it. All right. The blue line next. Y-intercept's 4. 1, 2, 3, 4. My slope is -1. It's a solid line. This time I paid attention. And if I test the origin, is 0 less than or equal to 4? Yes. So I want that to be part of the solution. Okay, last but not least, I have a y-intercept of +4 and a slope of +1. Solid line. And if I test the 0, 0, it was true, so I want 0 to be part of my solution. My final solution is just that triangle in the middle. Awesome. Good work today.